Speaker is Professor Timur Sadykov, who recently moved to the Moscow Independent University, who will speak about monodromy of hypergeometric systems and analytic complexity of algebraic functions. As usual, we're going to take the speaker, in this case Professor Sadykov, out to dinner at the usual place. If you'd like to join us, let me know immediately after the talk. Thank you.
Thank you so much. I'm very thankful to the organizers for this seminar for inviting me to speak here, and to Mr. Sadykov for stimulating discussions. So I will discuss the notion of the so-called analytic complexity of special functions, and I will take a look at the relation of this notion to the monodromy of the so-called hypergeometric systems of partial differential equations. So to give some motivation for my talk, let me begin with recalling the statement of Hilbert's 13th problem, which goes as follows. Namely, Hilbert asked whether there existed, or possibly not, any continuous solutions to such an equation, such a septic algebraic equation, the equation of order 7, which could not be represented as superpositions, as any source of finite superpositions of continuous functions of two variables. Well, the reason that he was asking about that question about this particular equation is, of course, that it was then known that by means of the Chilling-House transformations, it was possible to reduce any equation of order 5 and 7, which could not be solved, of order 5 and 6, which could not be solved in the radicals, to simpler form, do some kind of reduction, which allowed one to actually express solutions as superpositions of bivariate analytic functions. And this equation was somehow the simplest possible equation for which it was not known whether it was possible or not to find such a decomposition, to find such an expression of x, which is looked at as a function of a, b, and c here, and which is implicitly defined by means of this algebraic equation. So whether it was possible or not to express it as a composition of continuous functions of merely two variables. And of course, there is the well-known theorem by Kolmogorov and Arnold from 1957, which states that actually any continuous functions of any number of variables, let's call it n, which is defined on a compact set in the real space, can be represented as a finite superposition of simply continuous functions of one variable and the addition. So actually, what this theorem states is that to obtain any continuous function in any number of variables, defined like that, you only need one bivariate function, which can be taken to be the addition, and of course, you also need all the continuous functions of one variable. And this was their solution to Hilbert's 13th problem, because Hilbert asked for continuous solutions to such an equation. And of course, you can easily ask for a more general question, namely whether it was possible to do the same kind of decomposition by means of representing a function as a superposition of a finite superposition of continuous functions of the variables for some other continuous functions defined by means of not necessarily through this equation, but somehow else. However, if you check the status of this problem on Wikipedia or elsewhere, then typically you will see that this problem is considered to be partially solved. And the reason is that there is a lot of dispute about what Hilbert actually meant by continuous functions. Well, in his talk, at the Mathematical Congress in 1900, he actually does ask for continuous solutions to such an equation. However, in the very next sentence, as it is known, he already speaks of analytic functions. And it is, of course, not a very natural class class of continuous functions is, of course, not a very natural class to consider when looking for solutions to such an algebraic equation, because it is, well, it defines a multivariate algebraic function which can be expanded into power series, which converge in suitable domains, and which is analytic on suitable sets. So it is kind of not quite natural to ask for continuous solutions. And there was, of course, also that shift in the terminology, namely in the early years and during some period of growth of complex analysis and function theory. People called functions continuous when we would actually say analytic, and so this has possibly caused some kind of misunderstanding. So this problem is considered by many people to be partially solved. And I will use it as a motivation for what I will talk about today. So another recent definition, which was given by Valery Beloshapka of Moscow State University in 2007, goes as follows. It attempts to somehow measure the complexity of a representation of a bivariate analytic function in terms of all possible compositions of univariate functions, and the addition, which was already special and appearing in Kolmogorov and Arnold's theorem. Namely, Beloshapka introduces classes of complexity for analytic functions of two variables in the following way. So he simply defines the complexity class with index 0 to consist of univariate functions of the two variables x and y, and the n plus 1 complexity class is being defined inductively to comprise the functions which can be represented as follows. We simply take functions a n, b n, bn, which are assumed to be in the nth complexity class, and we add them up using that special function addition, which is essentially the only bivariate analytic function appearing in this definition. And on the top of it, we apply a univariate function c. And by definition, the n plus 1 complexity class consists of all functions of this form. So with this inductive or recursive definition, we naturally have a chain of complexity classes like this, and of course we look at all functions of finite complexity. And if a function is not in this union, then we say that this complexity is it. So in a sense, Kolmogorov and Arnold's theorem states that in the continuous setup, any function of any number of variables has finite complexity. So there is always such a composition which represents that function. However, in the analytic case, it can be relatively easily seen that there are, of course, functions of infinite analytic complexity. But just to begin with, let's look at this very simple example. For example, the beta function has analytic complexity equal to 2. And it is, of course, because it is a quotient of the product of the gammas of x and y, and the gamma of x plus y, and the function gamma of x plus y is, of course, a function of complexity 1. So a typical representative of the first complexity class is simply a function of the form of x and y, which is defined to be, according to the inductive definition, as the sum of a function of complexity 0, which we call a, and a function of another function, and another function of complexity 0, which we call b, and on the top of it we take some other function c, and this is a typical representative of the first complexity class. So for this reason, it is easily seen that gamma of x plus y is of complexity 1, and so is gamma of x multiplied with gamma of y, because in fact it is unimportant which arithmetic operation we use, addition or multiplication or division, they all lead to the same chain of complexity classes. And when we take the quotient, we still have one more step to go, and that is the so beta function is a function of complexity 2. However, there exist lots of functions whose analytic complexity is infinite, and they have been classically known for different reasons. But already in 1920, Ostrovsky proved essentially that the generalized Riemann zeta function, which is defined like this, we make a power series out of the definition for the zeta function, and it has infinite analytic complexity. And what Ostrovsky actually proved, inspired in fact by another question of Hilbert, asked himself at the Mathematical Congress in 1900, what he proved was that there is no differential polynomial, that is a polynomial with constant coefficients in the function itself and all of its derivatives, which can possibly be satisfied by this generalized zeta function. And we'll see in a moment that it actually means that this function has infinite analytic complexity. So, indeed, just as I wrote before, a typical representative of the first complexity class is a function of this form. And it is very easy to derive a simple differential equation which is necessarily satisfied by any function of this form. Namely, if we take the quotient of the partials of f with respect to x and y, then we get rid of the c function.
Can I make a comment for Western people? We don't usually have primes. We just put subscripts.
Oh,
so
right.
This means the derivative of f with respect to x.
Oh, right.
We don't usually put primes.
Okay, okay.
For partial derivatives.
Yeah. So what I mean is simply the quotient of partials.
Yeah.
So the derivative of f with respect to x divided by the derivative of f with respect to y, and we take the logarithm to separate them apart, and then we simply differentiate with respect to x and y. And we clearly get 0 because the quotient is simply a prime over b prime, and those are univariate functions depending on x and y only. So this is the equation, one of the equations satisfied by any function in the first complexity class. And of course, we will say that the analytic complexity of a function is exactly equal to n if it lies in the nth complexity class and does not lie in the n minus first complexity class. And if we develop the left-hand side of this equation and take the numerator, then we obtain that differential polynomial. So this is a differential polynomial satisfied by any function of complexity 1. And as we see, so it's actually a trinomial, and it has differential order 3 and algebraic order 4. And in fact, this polynomial, which I call delta 1 of f, vanishes if and only if f is in the first complexity class. So a proposition, which was proved by Shapka himself, goes as follows. For any n and the associated class of complexities, of complexity for analytic functions, there exists a differential polynomial delta n of f, which vanishes if and only if f is in that complexity class, and the initial definition, which is of course completely local, so for the moment we just disregard all issues like multivalueness of those functions for natural domains of holomorphy for the functions, but the definition, which is completely local, is also can be extended naturally by means of analytic continuation. So if a germ of an analytic function satisfies such a differential polynomial, then necessarily any germ of the function will also satisfy that equation. And just as I said, the order of complexity is defined to be n if and only if delta n of f vanishes while delta n minus 1 of f does not vanish for that function f. So this gives an integer number, the order of complexity, associated with every analytic function, which is defined as a composition, for example, of this form, possibly much more complicated. And of course, we assume that all those compositions make sense and that the functions which appear are analytic in suitable domains, so that that composition is well defined. And typically, if we say, pick an analytic function of the variables at random, it will have infinite analytic complexity. So it is, of course, possible to show that if we equip the set of all analytic functions defined on some suitable set with an irreducible topology, then the class of functions of finite complexity, that union of complexity classes over here, is going to be a very small set. It's going to be a countable union of nowhere dense sets. So a typical representative will have infinite analytic complexity.
So it's unlikely for a random function to have finite.
Yes, yes, very unlikely.
So do you have any intuition about Hilbert's surface problem? Whether it's typical?
Well, I don't know. I don't really aim at trying to work on that, but I'm rather interested in efficient computation of that complexity, and also of complexity of the so-called hypergeometric functions. Well, this is a new definition, to the best of my knowledge, and even for polynomials, it's not really known how to efficiently compute their complexity. Because this approach, by means of differential polynomials, it doesn't really lead anywhere. It's really a complicated way of computing complexity, and in the following example, we see that the complexity of an algebraic function defined by an equation of high order can be relatively small. For example, if we take any monic trinomial like this, so if u, p and u are fixed, they are parameters, integers, and p is greater than q, while x and y are our variables, and we consider this equation as an implicit definition of the function f, which depends on x and y for q fixed p and q. And Bellashapka himself proved that such a function will always have complexity 2, despite of the fact that the expressions for some small values of p and q can be rather complicated. However, if we use not derivatives but some really suitable functions for such a representation, then it can always be there is always a representation of complexity 2. Well, there are various questions which arise, and some of them are as follows. So the first question that I would like to address is how to efficiently compute that differential polynomial delta n of f. And it turns out to be really difficult to compute even delta 2. Well, I will speak about this a bit later in more detail. Well, the next question, which is still unanswered, is it possible to determine the order of analytic complexity for a trinomial, for example, and other algebraic functions of infinite order of complexity? This is not known either. And even for polynomials, it can be a challenge to compute this order of complexity. Well, of course, theoretically, there exist lots of ways to compute those defining polynomials, those differential polynomials for complexity classes. And here, I do this simple example for delta 1. So in fact, it is really beneficial to make use of that Gromov's approach developed by Gromov and his many co-authors, which tells that it is somehow instructive and illuminating to look at a differential equation that you want to understand, that you want to solve, and to take its differential consequences, and then quite naively replace the derivatives or the functions which appear by new algebraic variables. So simply passing from a differential equation, or rather a system of equations, to a set of algebraic equations which define an algebraic variety with some suitable space, Cn over Pn. And it turns out that it is instructive to look at that variety, and somehow it captures essential information about the solutions to the initial differential equation. So from this point of view, it is not strange that if we simply look at the Grosvenor basis, everything is commutative here, of the following ideal, so this is actually a command in Mathematica, of the ideal, which is defined like this. And this is simply what we get if we take this general representative, this generic representative of the first complexity class, and take all derivatives that are necessary, which in this case are all derivatives of order up to 3. And I simply call the derivatives of the functions a, b, and c that appear by a1, a2, a3, and so on. So the indices here actually indicate the differentiation. But we call them new variables. So for that reason, I don't write derivatives, and I simply write the sub-indices. And it is sufficient to take that many derivatives. And if we want to eliminate a's, b's, and c's like this out of these relations, then what we get is precisely the differential polynomial delta 1. So the polynomial in fx, y, fy, and so on, fx, y,
So you
y.
can do something analogous for delta 2, but it's much more complicated.
Well, you can do exactly the same thing, precisely the same thing, by simply taking sufficiently many derivatives. Well, you will need lots of them, well, up to order 11, I believe. And you need to eliminate all these, eliminate commutatively. So this is a completely standard commutative elimination, and you commutatively eliminate all these derivatives. And what you're left with is, it would be delta 2. Well, however, the complexity of such an elimination is, well, it's really heavy. And we have had really good computers, well, in fact, supercomputers, on this problem for quite a while, but this does not seem to take us anywhere. Well, another example of a function of an intermediate class of complexity and the corresponding representative of xy, which is like this. Well, it somehow gives a sense of how complicated this can be. Namely, if we only extend that general representative of the first complexity class by a single function. So instead of f like this, we consider a function f, which defined like this by means of 4 univariate analytic functions. Then we call it delta 1.5 of f, and the corresponding differential polynomial is of differential order 5, algebraic order 10, and consists of 17 monomials, and is highly non-trivial to compute. So this is a computational challenge.
So for this you do have the answer.
Yes, yes, in this case we do have the answer. Right. Okay, so this is somehow supposed to convince you that it is useful to look at the differential consequences, both linear and nonlinear, of differential equations satisfied by even algebraic functions. So algebraic because of Hilbert, and differential consequences because of complexity classes. And of course, a natural class of functions to look at is the class of the Nielsen class of univariate functions. That is, by definition, we think of these functions as having finite determination and moderate growth. So just as usually, by finite determination, I mean that the terms of a function at a generic non-singular point span over the complex numbers a finite dimensional space. And moderate growth is at most polynomial growth in any neighborhood of the singularity. So this is most easily clarified by an example. For example, the determination of any rational function, which is a quotient of polynomials, or of any function, of any single valued function, is simply 1, because there's only one term at any point. And it naturally satisfies a first order linear differential equation with polynomial coefficients. For a function of the form x to a, which has branching at the origin and possibly at infinity, the determination is also equal to 1 because any analytic continuation is a multiple of that principal branch. So we're still in the same linear space. The function logarithm of x has determination 2 because any term is, of course, well, any branch has the form log x plus 2 pi I k and this is in the linear span of 1 on and the principal branch log of x, and the corresponding differential equation, the linear differential equation, is of order 2, and this Fuchsian. And to give a less trivial example, we're going to look at the algebraic equation, the quintic, very much reduced quintic of this form, and now its determination of f as a function of x, where a is a parameter. So a is different from 0 here. It has determination 4, and this is the corresponding differential equation. Well, finally, the reciprocal of the logarithm of x has infinite determination, since there is no linear relation between the branches. So it is quite straightforward to see that for any function in the Nielsen class, there is a polynomial, there is a differential equation, a linear differential equation with polynomial coefficients, whose solution space is spanned precisely by the gerbs of that function, only branches of the function not at a generic point. So this is one class of equations that we're looking at. Now, another way of looking at algebraic functions, and in some cases understanding their complexity, is by using the Mayer's system of differential equations, which is satisfied by a given algebraic function determined by a generic algebraic curve. So by generic here, I mean that we have a univariate polynomial in f, and again, f is thought of as being implicitly defined by this relation, and the coefficients are just generic variables, xn, xn-1, so on x1 and x0, and it is classically known that there is a system of differential equations, in fact, a holomorphic system of linear partial and homogeneous differential equations, which is satisfied precisely by the branches of the function f. So it has appeared in 1937, and this is sort of the baby version of the Gelfand, Kapranov, and Zelinsky system of differential equations. So if you generalize to any lattice and any vector of parameters, then what you get out of this is clearly the Gelfand, Kapranov, and Zelinsky system of differential equations of hypergeometric type. This is the analog of the toric operators, and these are the homogeneities defined by a matrix. So this will be another class of systems, quite natural systems to look at, which now have all branches of a given algebraic function as its solutions. And also, there is, of course, lots of nonlinear equations satisfied by a given algebraic function. For example, a fairly nice looking and simple differential equation, nonlinear differential equation for such a function is given by the Hopf equation. So the equation of the partials of the function f satisfying an algebraic equation like this will necessarily be the power of the function itself. And this equation is very important in mathematical physics. It has been extensively studied in relation with gas and fluid dynamics. But I won't so much speak about this particular class of functions and equations. All right, so for understanding complexity, we would like to be able to find a suitable differential equation satisfied by a function in question, analyze its properties, and draw conclusions. And in fact, we can ask for much more than just the correct set of solutions. We can also prescribe branching of that solutions, and we can namely pose the following question. Suppose that we have a complete information about the branching of the solutions to a Fuchsian differential equation. So is it somehow possible to go back and having all that information, construct a Fuchsian differential equation? So instead of solving a differential equation, I'd like to go back and having the prescribed information about branching, which in algebraic case is simply the information about some sort of permutations of a finite set, because as we analytically consider an algebraic function, the sheets on the given surface simply interchange. So that's why we have permutations. And this is the information about the monodromy. And also we are given prescribed singularities. This is not